Welcome to the third lecture video in our second class time series of lecture videos. We ended the second one with some discussion of kinetic versus thermodynamic control of reactions and a discussion of the Arrhenius equation to try to get a sense of if you have a reaction that's kinetically controlled, what's the energy difference in terms of activation energies that will lead to a 10 to 1 difference in products, and that was only 1.4 kcals per mole. Every physical organic chemist probably has that tattooed somewhere on them. Of course, it's logarithmic, so a 2.8 kcal per mole difference would lead to 100 to 1 selectivity, and so on and so forth. So it's really small differences in activation energies for competing pathways that give rise to, widely varying product distributions. To illustrate kinetic control, let's consider the hydrolysis of 1,chloro-2-butene at low temperatures. That's another thing. Reactions typically low temperatures and can have an inclination towards kinetic control if there's a difference in activation energies for competing pathways. So recall that primary allylic halides can do SN1 reactions. Here we've got our 1,chloro-2-butene. If we throw this in water, at ice water temperatures of 0 degrees C, we'll go ahead and pop the chloride off and we form this allylic carbocation, right? This is a primary allylic carbocation. Of course, there's another resonance form associated with it. That is a secondary allylic carbocation. This particular carbocation is going to be more stable, right? Secondary carbocations are more stable than primary. And they're both allylic, so that factor is already baked into the cake. And so here we have water either attacking our primary carbon or our secondary carbocation center. So you could think of this secondary carbocation center going with some reaction rate constant K1 and this primary carbocation center going with some rate constant K2. And once water adds in, then it will be deprotonated. I don't mind if you draw that mechanism using a lone pair on water. This is the preferred way to deprotonate under these conditions, because if you use chloride, you just generate HCl, and HCl in water simply dissociates. And so the end result of these reactions are allylic alcohols. So, and of course, HCl in water, which is H3O plus and Cl minus, or we say HCl, right, in water. In this reaction and in these conditions, our major product is the less thermodynamically stable alkene. So it's only a monoalkyl substituted alkene instead of this dialkyl substituted alkene, which is the more stable product, right? But it's a secondary alcohol. So that means the water reacted with the secondary allylic carbocation, which is the more stable intermediate. Because the stability of that intermediate is electronic versus, substitutions of the alkenes. So, of course, we do get a minor product of the more thermodynamically stable dialkyl substituted alkene. Let's look at a energy versus reaction coordinate diagram for this reaction. The secondary allylic carbocation is more stable than the primary allylic carbocation, right? That's what's to say, or how your text presents it, is the secondary allylic carbocation has a smaller activation energy hill to climb in its reaction with water versus this primary allylic carbocation, which has this larger activation energy hill to climb. Hence, the transition state for our secondary carbocation, we'll call that EA secondary, is lower in energy than the activation energy EA for the primary carbocation. And here are, hypothetical transition state structures for our reaction of this carbocation with water. But of course, in terms of stability of the resulting alcohol, we know that our dialkyl substituted alcohol is going to be more stable, that is lower in energy, right, than our monoalkyl substituted alcohol. Of course, if the reaction is under kinetic control, that means, geez, it's easier to climb the smaller hill. Even though we're forming a less stable product, we'll form more of it faster. At this 0 degree temperature, right, than the more stable alkene. So hopefully this energy versus reaction coordinate diagram helps clarify, what's going on in this reaction that's under kinetic control under these conditions. So here we go. What are the percentages of products at the end of the reaction? Well, at 0 degrees C in water under kinetic control, we get about 70% of our secondary alcohol kinetic product, right, versus 30% of our dialkyl substituted primary allylic alcohol thermodynamic product, right? And you could, estimate the ratio of those percentages as the ratio of those reaction rate constants. So the final, secondary allylic alcohol concentration to the final primary allylic alcohol concentration, 70 to 30, is about, the ratio of those reaction rate constants, which equals E to the difference in activation energy over RT for the process, right? And you could, at 0 degrees, calculate that out knowing what R is, 1.9872 cals per mole K. And temperature is 273.15 Kelvin at 0 degrees C, right? And so that difference in activation energy is really small, 0.46 kcals per mole, but wow, it gives us a 70-30 distribution, right? What's interesting is that if you ran this reaction at 50 degrees C, now you're under thermodynamic control. So you get only 15% of the secondary allylic alcohol and 85% of the primary allylic alcohol. Now that, reaction is, being done at high temperatures, typically those favor thermodynamic control of your reaction if you have competing pathways, particularly ones with such small, differences in activation energy. So I hope that helps wrap your mind around these, kinetic versus thermodynamic control of reactions. We'll be seeing a lot of other cases. We've looked at a radical reaction case. We just looked at a carbocation case. We'll see more cases as we continue in, our semester of class time lectures. I'll see you for the next video.